In this problem, a car is traveling at a constant velocity of 10 meters per second. The problem gives us an initial position for the car of 100 meters. We're asked to plot the acceleration versus time and the velocity versus time. Later, we'll plot the position versus time too. So there's a reason that the graphs have been stacked in this order. We like to put the original function on top, which is going to be the position. And then we're going to put what is called the first derivative underneath that. That's the velocity function, of course. And what we're going to do with the acceleration is that's going to be the derivative of the derivative. It's called a second derivative. And all the same rules we use to turn an original function into a first derivative, we'll use those same rules to turn the first derivative into the second derivative. All right, so let's see how this one works. First thing we can do is just plot some of the given information. They say that it's going to travel at a constant velocity of plus 10, which means that the velocity is going to stay 10 throughout time. It's not going to change. So we need a horizontal line for that. Okay, we're also told that this car starts off at a position of 100 meters. So that would be this point here. And now, since we're being asked to plot the acceleration, we just need a derivative of the velocity. So what's the derivative of a constant 10? I'll write it down here. A equals dv over dt. Take the derivative of 10 and you get 0. There's actually no acceleration in this problem. When an object travels with constant velocity, there's no change in the velocity with time. But acceleration is defined as a change in velocity with time. So here we have no acceleration. All right, let's look at number 2 now. 2 says, for this question, let t equals 0 be the initial time, and choose a final time of t equals 10 seconds. We want to shade the area underneath the velocity curve between t equals 0 and t equals 10. The signed area under the curve will be equal to the displacement of the car from t equals 0 to 10. So let's shade that area. All right, now we're supposed to use the area of a rectangle formula to find the displacement of the car. So let's take a look at the dimensions of that rectangle. It's got a width and a height. Now the height is given by v, the velocity. And the width is given by some change in time, delta t. So it was Sir Isaac Newton, famous physicist and mathematician, who discovered the relationship between these graphs. And he discovered the mathematics of calculus to describe them as well. His great insight was that if we were to multiply a velocity times a time, then the area under that curve would have meaning. It would be the displacement of the object. And so there's a formula in physics for this which says delta x equals v times t. And if we can just multiply those two things, then we'll know how far the car has traveled. So let's go ahead and plug in the numbers now. It's a 10 meter per second speed, and it lasted for 10 seconds. So how far did the car travel? 100 meters. Now this delta x is neither an initial nor final position. It's a change in the position. It's a change in the graph above. So in our graph above, we started off with an initial position of 100. And then from there has to be an addition of another 100. And by 10 seconds later, we'll now be located at this new position, which is called x final. The formula for figuring out how you get from the initial to the final is xi plus delta x equals xf. An initial value plus a change equals the final value. One of the most fundamental formulas in science and math. So we're going to start off with 100 meters initially. That's where we're located. We found through the mathematics above that we were going to have a displacement or change of 100. And that takes us to 200. And that's our final location.